Hi, good day. So today we will be covering chapter 3 on DC machine. Particularly, we will be seeing the DC motors. Okay, so this is an example of a DC motor, so which we can buy from the shop. Okay, usually it will be in this packaging, but when we open it, so there will be many parts inside. So this is the housing. So there will be a permanent magnet. There will be stator. There will be winding, copper wire. So the current DC motor come with the all IC, which can detect the rotational position, and we have a back housing. So this is a combination of all the components inside the DC motor. Okay, so when we are talking about DC motor, one important concept is the counter electromotive force or CEMF. The armature has a resistance R. Okay, so resistance inside here, and it has a magnetic field. Is created by a set of permanent magnet. So earlier we have seen. So there's a permanent magnet inside which can create a magnetic field inside this coil. Okay, so as soon as the switch is connected, so when we connect the switch, a large current flows inside, and the armature begin to rotate because of the flux being cut. So the magnetic field will be generated, and it will go and go around until the armature become more more faster. So move faster due to the large current flow. So the force created by the current and the permanent magnet. So these forces added up to produce a powerful torque, causing the armature to rotate. So the armature will always will be rotating. Okay, and the rotation is not an important thing, but it must produce enough torque to do whatever work for us. So let's say, for example, we want to attach the motor to a car. So a car power window. So usually power window we know there's a motor to move the mirror up and down. So we need to have powerful torque to pull the mirror up and down. So if torque is not enough, it will not go up or go down, uh, and the motor will be spoiled due to overheating. Okay, so the induced voltage E0 is proportional to the speed of the rotation. So induced voltage is inside. Okay, is proportional. So it's directly proportional, meaning when the speed is increased or the impedance is increased or the flux is increased, the induced voltage is zero inside will also increase. Okay, so the induced voltage E0 is called counter electromotive force, or we call it as a CEMF. So we also call it as a back EMF because the polarity always acts against the source. So when you're positive, you also will be positive. So it won't like go from. So sometimes will be difficult to understand how it travel from positive to positive, but it is because of the polarity keep on changing and changing inside to make the motor rotates. Okay, so as a summary, we can see from here. So ES, the supply E, and also the EO is not E0, is EO. So output E voltage. So when we minus it, that is the net voltage that is acting. Okay, so acceleration of the motor. So it's an important part because we want the motor to accelerate uniformly without any jerk, without any sudden changes. So the net voltage acting in the armature circuit is ES minus E0. So the resulting armature current I, so I equals to ES over minus E0 over R. When the motor is at rest, E0, uh, EO is 0. Okay, so when we replace 0 here, we can get IA equals to ES over R. So as the speed increases, EO increases. When speed increases, EO increases. When EO increases, this value will become almost zero. Okay, almost zero. Here the armature of a permanent magnet DC generator has a resistance of 1 ohm, so is the example, and generate a voltage of 50 volt when the speed is 500 revolution per minute. So if the armature is connected to the source of 150 volt, so calculate the starting current. So we calculate the starting current. So at the moment of startup, the armature is stationary, so EO equals to 0 volt. Thus, the starting current is limited only by the armature resistance. Okay, so equals to ES over R. So no EO. So ES is 150 volt. R is 1 ohm. So it is 150 ampere. So that is the first part. Second part. So we need to calculate the counter EMF when the motor runs at 1000 RPM. So we find ourselves for the value of 1460. Okay. So because the generator voltage is 50 volt at 500 revolution per minute, so the CEMF for the motor will be 100 volt for 1000 RPM because it's directly proportional. So 50 volt produce 500, 100 volts produce 1000. So under 46 volt supposed to produce 1460 revolution per minute. So there's a note here: CEMF increases as the speed increases. Okay, so that's the second part. And the third part, calculate the armature current at 1000 RPM. So find yourself if value is 1460. So the net voltage in the armature circuit is 1000 revolution per minute. So ES minus E0, so 150 minus 100 equals to 50. The corresponding armature current is, so I for N equals to 1000. So ES minus E0 over R, so 50. So here 50 over R1 equals to 50 ampere. So try to find yourself for this. So mechanical power and torque. So mechanical power and torque are very important in a DC motor because we want to utilize the power and also we want to get the maximum torque possible. Okay, so the counter electromotive force CEMF induced in a lap on armature. So this is the formula for EMF. E0 equals to Zn phi over 60. The electrical power PA supplied to the armature is equal to the supply voltage ES multiplied by the armature current. So PA equals to ES times I. So this is from the formula P equals to VI. The power is very important, so I remember it as this. So P equals to VI. Power is very important. Okay, so we can see here. We can get the similar formula. So PA equals to ES times with I. So ES is equals to the sum of E0 plus IR. So this is from the previous formula. So we can take this formula and substitute inside here. So we can get this set of formula. So PA equals to ES times EI. So here, so equals to E0 plus IR times I. Then we expand it, we can get E0, so EOI plus I square R. Okay, so there are two components of power. So I square R is the heat dissipated in the armature. Okay, because when the motor rotates, the armature will become hot and also the heat will be dissipated. So I square R is the heat and EOI. Okay, so this part is the electrical power that is converted into mechanical power. So this is actually the mechanical power generated by the DC motor. Okay, so the mechanical power of the motor is P equals to EOI. Okay, so this is the explanation for the power. Okay, in the relation to with the torque T, so P equals to NT over 9.55. So we can can get this formula from chapter 1. Okay, so N is the speed of the rotation. So we can substitute the previous formula inside. So P equals to NT over 9.55 equals to uh, E0I. So we got it from the previous slide. Okay, so here. Okay, and it is also the same as ZNI 5 over 60. We got it from here. So E0 is this. So easy, sorry, EO is the previous formula. So EOI equals to ZNI 5 over 60. Okay, so we just take these two components, this part and this part, we rearrange, we can get this formula for T. T equals to Z phi I over 6.28. Okay, so all these are the explanation for the formula. Okay, so example 2, the following details are given on 2 to 5 kilowatt, 250 volt, 1200 revolution per minute DC motor. So all these are the specification of the DC motor. So we need to determine the rated armature current, the number of conductors per slot, and also the flux per pole. So we find for the first the rated armature current. So the rated armature current is I equals to P over E0. So P is 2 to 5,000 divided by 250. So the value of I is 900 ampere. So this from this formula. Okay, for lap winding, so the question mentioned it is a it's a lap winding. So for lap winding, so we need to understand each coil is made up of two conductors. So we need to find out so how many coils are there. So armature coils we have 243. So 243. So each coil has two conductors. The question asks to find the number of conductors. So we times this with 2. So we get 486 conductors. But the question asks the number of conductors per slot. So here we have 81 armature slot. So we need to find for one. So we divide by 81. So each slot will have 6 conductors. Okay. C, we want to find the flux per pole. Okay, we find the torque first. So from this formula, so torque, we can just replace the values and we get the torque 1791 Newton meter. So once we find the torque, we can find the value. From this formula, we rearrange. We can get phi equals to 6.28 T over Zi. So we replace the values, we get 225.7 milliweber. Okay. So another important part of DC motor is the speed of rotation, how speed it rotates. Okay, when a DC motor drives a load between no load to full load, so meaning from 0 to 100, so the IR drops due to armature resistance is always small compared to the supply voltage ES. So when you increase the speed, E0 also increase, uh, so IR will drop. Okay, so IR will drop. Okay, so CEMF EO is nearly equals to ES as ES equals to E0 plus IR. So this R will become very small. Okay, almost zero. So it will become zero. So it will become almost the same, nearly equal. Okay, so EO equals to Zn phi over 60. So when we replace EO with ES, so we can get this formula. So same. So ES equals to Zn phi over 60. So N, so we rearrange this, we can get N equals to 60 ES over Z phi. So all these are the informations. Okay, so armature speed control. So according to N equals to 60 ES over Z phi. So the earliest formula we derived. So if the flux per pole is kept constant, so flux you make it constant. The speed depends only on the armature speed ES. So it only depends because usually Z will be fixed as well. So it only depend on ES. So when we increase the supply voltage, so the motor will increase, motor speed will increase. So that's why we directly connect DC motor to a battery. When we increase the power of the, we increase the voltage of the battery, we can see the DC motor rotates faster because of this principle. Okay, so in practice, ES can be varied by connecting a motor armature amp to a separately excited variable DC generator. The field excitation permanent magnet of the motor is kept constant, but the generator excitation IX can be varied from 0 to maximum and even reverse. So the generator is driven by a AC motor connected to a three-phase line. So if we can see, so we have this system. So the system, it has two generators. So this is the field generators, and this is uh, another generator. So which is connected. So this is fixed usually, but for this, so we can vary the variables. Okay, so when we control it, we vary the supply. Uh, so this is connected to a three phase, so we can have three sine wave for us to utilize. So we don't need to change anything in the actual setup, but by adding one separately excited variable DC generator, so we can vary the voltage that is supplied to this. Okay, so ES we can vary. Okay, so the generator is driven by AC motor connected to a three-phase line. So by doing this, it will happen? We can increase the speed and reduce and even reverse it. Okay, so we no need to make any changes to the actual setup. So that is the reason why we can see most of the adapters. So we have a supply voltage of 240 volt in our uh, electrical switch. Okay, switch. So when we plug in our adapter, so in the adapter and even in our laptop, we can have this kind of variable changes. Okay, variable DC generators. We can play around with the voltage in order to give us a suitable voltage that we want. Okay, so example 3. A 2000 kilowatt 500 volt variable speed motor is driven by a 2500 kilowatt generator using a watt Leonard control. So the previous method is known as watt Leonard system. So what Leonard said, we don't need to make any big changes to the actual system, but by adding a small independent separate excited variable DC generator, so we can play around with the voltage. So that is the current method of speed control by Watt Leonard system. Okay, so we use this in our daily life, and in this question, so they are using this Watt Leonard control system. So the total resistance of the motor and generator armature circuit is 10 milli ohm. The motor turns at nominal speed of 300 revolution per minute when EO is 500 volt. So calculate the motor torque and speed when ES equals to 400 volt and E0 equals to 380, and they give another situation. So here we can see E0 are the same, 380, 380, only ES is changing. So we see the solution. The armature current I equals to ES minus EO over R. So 400 minus 380 over 10 milli. So we can get 20 over 0.01. So the armature current is 2000 ampere. So the power to the motor armature at EO equals to 380. So power equals to E0 I. So 380 times 2000 is 760 kilowatt. And the motor speed at AEO equals to 380 volt. So we replace in the N formula we developed before. So N equals to 380 over 500 times 300. So we get 228 revolution per minute. And the motor torque at EO equals to 380 volt. So T equals to 9.55. So this is the top formula, 9.55 P over N. So we get, after we solve it, we get 31.8 kilonewton meter. Okay, so the second, so they give 350 ES and E0 is 380. So since E0 is 380 for this case, so the motor speed is still 228 revolution per minute. So the only thing that will change is the armature current, because E0 now, ES now is 350. So we get a negative. So negative 3000 ampere. So negative, uh, meaning in the electrical, is only flowing in the reverse direction. So it's not carrying any significance other than the reversal direction control. So when we want to use it in a calculation, we don't need to put negative. Okay, so the power to the motor armature is P equals to E0I, EOI. So 380 times 3000, so we get 1140 kilowatt. So we replace this inside the braking torque by the motor is T equals to 9.55 power times power over n. So we replace all this. So we get the value is 47.8 kilonewton meter. Okay, so field speed control, the shunt motor. Shunt means parallel. So the motor that is connected in parallel. Okay, so we can have a shunt field to control it. So according to CEMF, EO equals to Z n phi over 60 and n. So when we rearrange this, we can get this formula. The speed of the DC motor can be varied by the varying the field flux. So when we vary this, so we can vary the value, the speed of the motor. Okay. So to control the field flux, the rheostat RF is connected in series with the field. So we have a shunt field and we have a rheostat. Rheostat is like a potentiometer. We can control the value of the resistance. Okay, so we can see an example. The shunt motor rotating at 1500 revolution per minute is fed by the 120 volt source. The line current is 51 ampere and the shunt field resistance is 120 ohm. If the armature resistance is 0.1 ohm, determine the following. A. The current is in the armature. So we find the current first. So the field current, yeah, X equals to 120 over 120, so 1 ampere. So the armature current is, so earlier is given. So the line current is 51. So we need to minus with the field current 1. So 51 ampere minus 1 ampere is 50 ampere. Okay, second we need to determine the counter EMF. So the voltage across the armature is 120 volt. Voltage drop due to the armature resistance V equals to IR. So I we already know the armature current is 50 ampere. Resistance is 0.1. So V equals to 5 volt. So the back EMF or CEMF generated by the armature is 120 minus 5 because that's the differential. So is 115 volt. Okay, the total power supplied to the motor. So PI equals to ES I. Okay, so ESI. We want to find the power supply. So 120 volt times 51 is 6120. The power absorbed by the armature. So PA equals to ESI. So 120 times 50. So 6000. So the power dissipated in the armature, so P equals to I square R. So 50 square times 1 is 250 watt. And the mechanical power developed in the armature is 6000 minus 250 because this is it dissipated from the system. So the mechanical power which fully utilized is 5000 to 750. Okay, series motor. So earlier we have seen the shunt motor which is connected in parallel. So this is a motor connected in series. So the field is series. Okay, it's not about the motor connecting in series. The field, the magnetic field generated is in a series. So a series motor is identical in construction to the shunt motor except for the field. The field is connected in series with the armature and carry the full armature current. Because when it's connected in series, uh, the motor can become very hot faster. So you need to have a few turns of wiring having a cross section sufficiently large to carry the current, because the current will be huge due to lesser resistance. And when in series, we know based on Kirchhoff law, the the current will be maximum. Okay, maximum for one circuit. So in this case, we need to have good wires, a few tons of wires with good cross section to sustain the current that will be supplied. Okay, so the differences between the shunt motor, the flux per pole is constant. Okay, at all loads, because the shunt field is connected in the line in parallel. Okay, the flux per pole is constant, but in series motor, the flux per pole is depending upon the armature current and upon the load. The starting torque of the series is greater than the shunt motors. Okay, so flux per pole uh, is our field. Is depending in series is depending on the armature current. So when we can control the armature current, we can control the field per pole. But in shunt motor, the flux per pole is constant, so it doesn't matter whether the current is sufficient or not. So whether it's managed well or not, so it still can be used. So shunt motor and series motor, it has its own advantages. So we need to determine so when to use. Okay. So example 5 and 15 HP horsepower. So 1 horsepower is 746 watt. Okay, so this is 15 horsepower. So 240 volt 1780 revolution per minute DC series motor has a full load current of 54 ampere. Its operating characteristics are given by per unit curve as in the figure. Okay, so we need to determine the current and the speed when load current is 24 Newton meter. Okay, so we see the first part first, the current and the speed. So we need to establish the base power, base speed, and base current of the motor. So base power is 15 HP. So 15 times 746 is 11190 watt. Okay, and Newton, revolution. In revolution, we want to find it RPM. Is given 1780. Okay, so it's given. So IB is 50. So current base current. So we want to calculate the base torque. Base torque is 9.55 times PB over MB. So it's here. So 9.55 times 11190 over 1780. So torque is 60 Newton meter. So when the load torque, so you say when load torque is 24 Newton meter. Okay, corresponding uh, to per unit torque, because only per unit torque is given. So on this curve, so this is a PU curve, chapter 1. Okay, so we want to find when the load torque is uh, 24 Newton meter. So we can see here. So TPU, so torque per unit. So here we know uh, it is 60. Base torque is 60. So we want to find for 24 Newton meter. So 24 over 60 is 0.4. So referring to the figure, when T is at 0.4 pu, so we can see. So this is torque versus current curve. So we want to find. So when T equals to 0.4. So here, this point, when t is 0.4, uh, speed and also armature current. So we can see we are interested in armature current. Armature current is 0.6. Okay, here 0.6. Okay, so when T is 0.4 pu, the current is 0.6 pu. So IPU equals to I over IB. So we can calculate this. So we can find I equals to IPU times IB. So 0.6 times 54. So 54 is here. So it's 32.4 ampere. So to calculate the efficiency, we need to know the PO and PI. So PI equals to E0 EOI. So 240 times 32.4 is 7776 watt. So P output is NT over 9.55. So 2492 times 24 over 9.55. So we get 96263. So we want to find the efficiency. So PO over PI. So we solve it. We get 0.805. So or efficiency of 80.5 percentage. Okay. So all these example, please try first for you to understand step by step how to calculate. So all the examples are there. Okay. The last part for today, the compound motor. So the compound motor is actually a combination of both series and shunt. So you can see it has a series and also shunt parallel part. Similar here, it has a series and also shunt field connected. So it depends on our design. So we need to determine which one we want to use. Okay, so with this, thank you.